Yes, sir.
So,
Dinesh sir, how many participants are joining?
Yeah, they're joining, sir. 2 minutes. That's what I told,
double
sir.
digit. Okay, say double digit. No, they are in double digit. No problem. Say like that.
Yes, sir,
Early
yes,
days
sir.
that Mati Muni was there. Now that this is why is earning in 4 digits. No, they never tell the fixed salary. No. So similarly, don't
Yes,
tell the
sir.
number of participants. Say that they are in double digit. Okay.
Ah.
So it can be anything between 10 to 100.
Ex-
Means 10 to 99.
Exactly, sir.
Number
Yeah.
is in
Exactly.
double digit. Okay. So double digit
Yes, sir.
number is good. No? Okay.
Yeah, that
Right? It is not a single digit number. Okay. Although I have given talk in a single digit audience also, where only suppose 4 or 5 people are there. So
Oh,
just 1 minute. Let me just attend one call. Hello?
Yes, sir.
yeah, yeah.
Hello. Yes. Hello.
So, Dinesh sir, right now, number of participants would be more than 20.
Yeah. Sir, they're like participants. Once the time starts, they will join.
Okay. Yeah, it's 11:31. That's good. Actually, sir has there is a associate in another lectures. Just now, sir finished it up.
किसका लेक्चर था?
सर आपका भी और एक
वो
लेक्चर में
तो
शायद
मॉर्निंग में
क्लास में थे
रेगुलर
आप।
था वो तो दैट वाज 9 to 10
Okay,
10
okay,
I
okay.
finished है ना वो तो अलग है. I think a lot of
Oh.
participants have joined. I think we can
Yes.
maybe
Yeah.
we can start otherwise जो है because
Yes, sir. We'll start.
2:30 there is a PhD Viva at IIT Madras. Okay.
Okay, sir.
I
We'll
have
start, sir.
IIT Madras also.
So Dinesh sir, please introduce sir.
Yeah.
Yes. Okay. Yes.
Yes.
Vanakkam and welcome to the day 4 session 2. This motivation lecture will be delivered by Professor Uday Shankar Dixit from IIT Guwahati. A few words about Professor Uday Shankar Dixit. Professor Dixit completed his PhD from Indian Institute of Technology Kanpur and joined as lecturer in IIT Guwahati at 1998. Before joining IIT Guwahati, he was working as engineer in HMP Pinjore and Indomax Steel Technology Delhi for around 4 years. His area of interest are plasticity, metal forming, laser-based manufacturing, finite element modeling, and optimization. As principal investigator and co-investigator, he has carried out around 19 sponsored projects. He has guided 12 PhD, 44 masters, and 38 batch of bachelors. Currently, 8 PhD, 4 MTech batches and are on roll. He has published around 14 books, 27 book chapters, 115 journals, 110 conferences. He served as BOG member for top institutes like IIT Kanpur, IGNIS, and also editorial board member in 10 international journals. He has organized and delivered talk in 100 plus short-term courses and guest lecture across the globe. He also acts as a reviewer of 10 plus top international journals. He has organized 6 conferences. He is also acting as vice president in the NAC AMTDR and also advisor of 8th International and 29th All India Manufacturing Technology Design and Research Conference to be held in PG College of Technology, Coimbatore during December 2021. With this brief intro, I request Professor Uday Shankar Dixit to motivate the participant towards additive manufacturing. Over to you, sir.
Okay. Thank you. I think I must share my slides. Okay. Have you given me permission? I think that because I joined as a guest, can I share? Okay.
Yes,
sir.
Share. Okay. Okay. So share means you have to share entire screen. Okay.
Yes,
You are
yes.
sharing your screen. Fine. Okay. So my screen will be seen. Okay.
Yes,
Let
sir.
me just go to that one. Okay. Fine. So this is yeah.
Yes, sir.
Right. I think it's okay. Yeah. So
Yes,
good morning to all the participants. Although I am not able to see your faces, and you are doing this course on the additive manufacturing. But now my talk will be somewhat like that of a skeptic person. Okay, that means I am not telling that everything is green or everything is rosy about 3D printing. So you know that I want to see critically, because this question I always ask, that will this additive manufacturing will be sustainable? Will it compete with the other processes? Do you think that after some time the other processes will not be there? It's a lot of, you know, that because a lot of media attention is being given to 3D printing. So you know, I just collected some catchy headlines from the media. Okay, that these are like 3D printed kidney gives hope to patients. Weekend Australian, August 8, 2021. But when I read the news in detail, then I find that this is means this is still far away. Okay, it is just a news, but it is okay. Scientists are doing, but it is not that in coming 3-4 years you will get a kidney like that you can replace. But this is this one, and then second is that what do we know about the first 3D printed house inaugurated in Germany? Okay, in Germany recently they inaugurated one house which is made by 3D printing. Okay, it's really good real house. But at other places, of course, they have made the house also. Means you can see lot of papers where you tell that they are making the 3D printed components and all these things. Then Mark forged launches aerospace ready composite 3D printing material. So this I am showing that even in the aerospace sector, lot of things are being made by 3D printers. Even GE, etc., they are quite active. Then NASA wants you to live on Mars, but within a 3D printed Martian habitat. Okay, so this is an application, process qualification, and more. So many issues are there. Then energy saving gas turbine from 3D printer. Okay, that is one thing. But then news attracted my attention because they are showing neutron sea internal stresses in components made by additive manufacturing. They are referring to neutron diffraction technique. Okay, by neutron diffraction you can find out the residual stresses. Okay, X-ray diffraction can also do, but neutron diffraction is much better. You can find out the inside also. So this gives us a, you know, clue that, you know, R is not well with 3D printing because energy, they are making gas turbine, but they get a lot of internal stresses also. So you have to, which are called residual stresses. So that means a lot of work has to be done. So the scope is wide open. That means you have to improve the mechanical performance and all that type of thing. So what happens that here, so the natural question is that is 3D printing sustainable? Now sustainability means economic aspect, environmental aspect, social aspect. All these things have to be considered together. And so there are a lot of issues that what will be the material, then how the components will be manufactured. Can it be after it is life is over, then can it be repaired? Can it be remanufactured? Can we do that upcycling, downcycling? That means we can enhance the quality of the product or we can use it as an inferior product. These many issues are there. So I say that there are, you know, two main pertinent questions, that what are the factors that need to be considered before purchasing a 3D printer. Okay, that is one thing. That how do you say that what factors should I consider? If I just want, I have an industry and I want to purchase a 3D printer, now which type of printer should I purchase? What should be its specification? Researchers have to pay attention to these type of questions also, that they should be. And based on the analysis of these factors, how can one assess the suitability of a 3D printer for the organization? Suppose you consider various factors, then how you can say that it will be useful? So 3D printing is with us since basically last 4-5 decades. In any product, you know, what happens, that product comes in the market, then there is a big hype. Okay, people get extra enthusiastic. Everybody starts doing the same thing. But after some time, the enthusiasm gets dampened, and maybe after some time it again comes. This has happened with many things, even things like neural network. In 40s, you know, neural network was very popular, and after that they were less popular. Then again they got prominence. in 90s, then again. So similarly, 3D printing also started, I would say, since 1974 or something like that, because there, what Matsubara of Mitsubishi company, he proposed a process with photohardening photopolymer resin. Okay, so what was done, that this resin, if it is exposed to some light, or light of some particular wavelength, then it will become hard. So based on this concept, later on the 3D printers were early, rapid prototyping machines were made. And typical photopolymers are acrylic and epoxy resin. Now in 1980s, Hideo Kodama and Charles Hull, they invented rapid prototyping. So 1980s, it was the time when I was doing my BTech, and that time, these things became very popular, that rapid prototyping, AutoCAD. So Dr. Hidoma Kodama, he applied for a Japanese patent on rapid prototyping, and in his concept, laser beam was used for curing the resin. But due to lack of funds, he could not do any practical work because he was not having this one funds. But Charles Hull of USA, he got a patent on stereolithography in 1986. Initially, he used UV lamps for curing resin. And then Charles Hull started 3D systems in 1986 in California. So in a way, that first 3D printing organization is by Charles Hull, and this is what this one. Okay, so this will be, yes, hello.
Yes, sir.
Yes, yes, it is
Yes, sir.
audible, sir.
Okay, yeah. So then 1992, okay, so this was, so what happens that if we see that laser, first this one is stereolithography. That was the first 3D printing, you can say, rapid prototyping. They used to say rapid prototyping because it was usually suitable for making only prototypes. Okay, otherwise, what is the practical utility? Because everywhere, even now, the steel dominates engineering products. So this was able to make by photopolymers. So here, what happens that they just nowadays, what is the concept that they have laser, then they focus through some lens, and there is a scanning mirror, and after that they cure, and then it becomes this one. Okay, so they can make the product. Okay. Now, due to usage of ultraviolet sensitive photopolymers in SLA, lasers used in SLA should have wavelength shorter than 400 nanometer. Okay, and both continuous wave and pulsed lasers can be used, and generally pulsed operation is more suitable for generating stronger UV power. Then in 1992, Stratasys developed huge deposition modeling, okay, FDM, and S. Scott Crump is considered as the inventor of FDM, and he is one of the co-founder of Stratasys. So you are seeing that these huge deposition-based machines, they have become very common, and many of them can be now purchased in 15,000, 20,000 also, or even less than that. They are available at Amazon. Some of my students have purchased this, and they are keeping these type of 3D printers in their rooms. So what happens that here, this is very convenient. In fact, it is basically, you can say, extrusion based, that this type of wire, in the wire form, there is material that, suppose this is ABS material, and this material is as a raw material, and it will get heated, and then it will melt, and then it will come through extruder. So this becomes very simple, and it is very inexpensive. You don't require any laser, etc. here. So in 1993, Sanders prototype introduced the first X-type inkjet 3D printer, and this is having this one. Okay, so in this, what they used to do that, in fact, the 3D printing name became more popular because of their product, in that there is a powder which will come, and from here that from printer some ink will come, and the ink will bind. Okay, you can have ink of different colors also, so it is just looking like a printer. Okay, so you know it will make a 3D object. Okay, that instead of paper printing, I am just printing like a 3D object. Okay, so it is, suppose you have this powder, so this is powder without binder, but in this portion binder has come. So wherever binder will go, it will bind the powder, and rest of the excess powder will be removed, and this will be this one. So this is a typically 3D printer, but nowadays in commercial sense, everything is called 3D printing. There is, but maybe proper term is nowadays additive manufacturing. Okay, additive manufacturing has very so many processes. In that one is this. So Sanders developed a large printer, that is Model Maker 3, and it was for industrial use. Okay. Now Sachs highlighted the potential of making metallic objects. Till then only polymer products were fabricated. So there is one paper by Sachs. It is published in 1990. There he has indicated that its name is three-dimensional printing, rapid pooling and prototypes directly from a CAD model. Okay, so they are talking about rapid pooling. That means you can even make a tool out of additive manufacturing or 3D printing, because you can do metallic printing. Okay, so since 1990, but generally after 2000 only, metallic printers became really common, and nowadays you can purchase, but they are very expensive. So in the metallic one, now you have, say, suppose selective laser sintering and selective laser melting. In selective laser sintering, it is a laser based powder based fusion technology. It was patented by Carl R. Deckard in year 1989. Here a high power laser beam, usually it can be CO2 laser, because CO2 laser is considered very robust, and it is having efficiency also between 10 to 15%. Otherwise, most of the lasers have very poor efficiency. That is one problem with the lasers. But nowadays, fiber lasers also have come. They have relatively better efficiency. Some of them may be having even 25% efficiency. So anyway, CO2 lasers are still common, and they fuse the powders, which may be made of polymers or some alloys, and then they, you know, that exports. So powder is there, but wherever the light will come, there will be that heating, and there will be sintering, and after that they will be sintered, and you can have. So then this diagram is showing that whole operation. That is fine, but a laser beam used for powder bed fusion process is based on the absorption of powder materials, and based on raw materials we have polymers. Generally we use CO2 laser whose wavelength is 10.6 micrometer, and but for metals we even use ND yarn, ND glass, and yttrium fiber laser, whose, you know, wavelength is less. So for these metals, they can absorb in a better way. So it is based on the absorption of the light. Now in the decade of 1980s, a lot of development took place in CAD. That was the beginning of the 3D rapid prototyping. AutoCAD was released in December 1982, and developments in CAD prompted the development of rapid prototyping. That is why, because they were making the drawings in the computer and then taking the printout, then the idea came that why we cannot take 3D output instead of 2D. So this happened in 1980s, but in 1990s, enthusiasm dampened. 80s was very full because of new technology, but the research and development continued, and faster and economical versions were developed. In 1996, Stratasys introduced the Genesis machine, which used an extrusion process similar to FDM. Okay, so and Aeromet was founded in 1997 as a subsidiary of MTS System. In March 1999, 3D systems introduced Thermojet. Okay, so these were some developments in 1990s. In 2000s, interest got renewed that in 21st century again we are talking about additive manufacturing because some new technologies were introduced. One thing is that electron beam melting technology was also patented. Instead of laser beam, one can use electron beam. Of course, machines will be expensive. Then in the 2005, use of fiber lasers in a cell system became common. And in 2008, even 3D concrete printing, that even concrete can be printed by this one. So civil engineering work can be done. That also started. So this is one 3D concrete printing, which you know that has been procured at IIT Guwahati. I think tomorrow Dr. Panda will give talk on that. I have seen that his session is there. So he has procured because his PhD was only in concrete printing. So concrete printing machine is there. It is simple. It is just like FDM only, but only thing that instead of melted plastic, in fact, concrete, cement, etc. is coming. So you see that they have printed IIT Guwahati by concrete actually. That after commissioning during commissioning of machine, so that is also getting this one. So one can make the house now by 3D printing. Okay, that means it can be done. So decade of 210s, some developments took place. 2017, Joule method of 3D printing by digital was introduced. Joule method means it is resistance heating. That means you have powder, but the current will be passed. So it will heat and it may sinter the material, or it can melt the material. And 2018, metal jet 3D printing system for metals by HP was launched. And desktop metal, again a metallic 3D printer was founded in 2015. So you see a lot of new companies have come in 2015, etc. Okay, so but the main issue remains everywhere that how sustainable is additive manufacturing. That means whether it will be economical. So first question is economical, then you worry about the environment, then you worry about the society, what will be the job scenario and all these type of things. So therefore, what I started doing that I said that, okay, let me focus more on sustainability aspect. And you see that, but before I tell something about that, I just summarize that these are the classification of additive manufacturing. It can be based on raw material. Some materials may use a solid type of material, right? That like suppose you have extrusion based this one, fuse deposition modeling, so I can have some rod type of thing which has to be melted. Or it can be laminated object manufacturing, that where you have sheets. They are just simple sheets. Sheets are produced very easily in industry, and you just have to cut it actually. That there will be by laser also you can cut in the particular portion, and then after that they can be bonded. So this is laminated object manufacturing. Why raw material is also very important, because you know some raw material will be costly. So maybe many times solid based materials are cheaper because it is very easy to manufacture a sheet. But suppose you want to make powder based, then you have to worry about powder. If I want to get iron powder, then I have to search here and there that where I will get powder. But if I want to purchase a rod, I can easily get. So powder based machines are like 3D printing, which we normally say, in which there is a powder and ink will act as a binder and then join. Then selective laser sintering, SLS process, selective laser melting, electron beam melting. All of them, they need powder. So if you want to find out the sustainability of these machines, you have to also pay attention that how powder is getting manufactured. And after that powder has been, some powder will get waste, how it will be utilized. Then liquid based all that like stereolithography and polyjet. Then based on this is the based on raw material, based on the layer formation, it can be extrusion based, sheet lamination, okay, beam deposition, powder based bed fusion, binder jet printing. Many methods can be there, even direct light technology. So some brief features that like powder bed fusion, you have selective laser sintering and selective laser melting. Usually SLM is used for metals and SLS is for even polymers and maybe low melting alloys, titanium alloys, ceramics, powders. There is a requirement of laser in these two. And direct energy deposition, which is one example, is laser engineered net shaping. You have to get, you can make functionally graded materials. You can have, you can make stainless steel, but there is a requirement of laser. Photopolymerization, which is called SLA, that is the first additive manufacturing SLA process. Plastic, glass, ceramic, laser is needed. Material extrusion, FDM. Here, raw material can be polycarbonate, ABS, PLA. Layer thickness may be 100 to 250. That is the limitation, but there is no requirement of laser. So that is one positive point, that laser is not needed. Sheet lamination, that is laminated object manufacturing, PVC sheet, aluminum sheet, layer thickness 80 to 200. Laser is needed. Binder jetting or 3D printing. Here raw material is powders. It can be metal oxide powder also. Laser is not needed here. So that means it is good that you have binder jet, but no laser is needed. And but you have to assess the properties of these, okay? Because laser is not needed, but whether that binder will give sufficient strength, these are the issues. Then material jet, material jetting. चल रही है class ना, you understand please ना? Okay. So material jetting, inkjet printing, acrylic powder, calcium carbonate. Okay, so this is here also you don't need any laser. So now the issue is that I have seen that very few people are doing that work in the cost estimation, but cost estimation is very important. You have to consider material cost, operator cost, slicing cost, overhead cost. So for developing a comprehensive cost model, you have to follow many things that like there are pre-processing, then you have to estimate time required for the process. Because if you want to do cost estimation, then you have to estimate the time also. And then you have to do that correct estimation of build time is a challenge. It is not very obvious that, okay, how much time will take. There are issues. Because, for example, in a SLS process, build time depends on many things, pre and post processing time also. Then what is many things you have to know about part geometry, cooling time, heating time. There are many issues about this one. And so the question is that we try to develop a build time estimation model. Okay, that means you have to follow much cycle. Suppose here you are doing 3D printing, but before that there is a powder delivery system. So this piston is there, it will force it, and then the powder will come here, and then the roller will pass through that, it will level that, then there will be scanning. So there are issues. So what happens that you have a typical time velocity diagram for roller is shown. Suppose you are manufacturing by layer. Now it depends that what is your path planning, whether you are going like this, then vertical, or you are going in the vertical way first, vertical means as per my screen, whether you are going in X direction or Y direction or zigzag path. And but the roller will accelerate, it will attain some velocity, and then after that it will retard. So this R type has to be R timing has to be calculated. So naturally that total time of this one, if we know the length, then we have to use proper formula based on the kinematics. I'm not going to explain it, but you have to say acceleration term also comes here. And this will be delay time between two layers, okay? Because one layer has been done, then roller stops, then again it will start. So there will be some delay, and this term hz by lt is basically what is the height and how many layers, what is the layer thickness. So more is the layer thickness, means lesser is the layer thickness, more time is needed. Okay, so that means this is, so you maybe you have to optimize. So that means as an engineer you have to think that if something can be made with thicker layers, then why to go for thinner layers? Okay, so this type of decision has to be taken. But so time required for sintering involves the time taken by the laser in scanning and rapid speed. This was for roller, that means for powder laying, and this is for the sintering process. There also the similar type of thing happens. You follow some path, and there is some scan spacing also, and then schematic of scanning process, sintering process is there, and then this codes, then time to, so here when you are doing scanning, because powder when it is labeling is done, then it is uniform. But when you are doing scanning, then depending on the product, your path will be very complicated. Maybe sometimes you are having some opening here. So from here to here, you can move at a slow speed, but here to here, you can move at a rapid speed. Okay, you can design that like this. So velocity profile is like this. From here to here, the speed is this, but after that rapid, because there is no material. Okay, but then that spacing will be very small. So if you just waste your time in accelerating, etc., then it may not be very justified, okay, to change your path. Okay, maybe that here, it in this case, it just could not attain the higher velocity, okay, because it went up to that, and then the path itself is very small. Okay, but if you have a large opening, then it is justified to raise it up to very high speed, and then after that it is moving at a constant speed, and then it comes down. So in the both the cases, calculations will be different. Okay, so these equations have been written, so these equations can be developed. Okay, now you can decide that whether it is space is small or big depending on the machine feature, and overall time is calculated like this. T build time is TMP, means time required for machine preparation. That involves machine setup. Because in SLS machine, what happens, the machine has to be heated also. It may take about half an hour. Whole powder has to be heated, brought to at some temperature. Okay, unnecessary that entire powder. But you know, I may need to make a small product, but I have a big machine, so entire this one. So warming up of the cloth chamber and other preliminary operations. So this work will go, and then there is similarly, this is also that some preparation time, and then scan time. This is for basically powder, and this is for scanning time. Okay, this is for powder preparation, and TR is the basically that some related to heating time, etc., and TEO. So TEO is time required in ending operations such as cooling down of the machine chamber and repositioning of the laser beam and powder bed. So for multiple parts, now build time becomes that this plus this divided by n, because powder also has to be laid once only. Okay, and after that you can make 2-3 product. So if you make more number of product, then machine preparation time, etc., is divided, but scan time and this time, okay, between two components, that time will remain basically this same depending on the product. So you have to decide that if in the same setup you can make many products, then I think the time required will be less. Then finally you can do cost calculation. All these details are in one paper. If you are interested, it was published in Journal of Mechanical Science and Technology, and it is about fuzzy set based cost model of additive manufacturing with a specific example of selective laser sintering. But similarly, one can make for other processes also. So here I am calculating the cost, operator cost, that what is its monthly salary, how much effectively he works, then slicing cost. So I am assuming that you have got a software nowadays, you can purchase things from a cloud. You need not have the hardware. That means online you can make the slicing, and monthly salary of designer, then overhead cost, machine cost has to be divided, machine cost minus salvage value divided by machine life. That means depreciation and annual maintenance cost, all those type of things have to be considered. Now the difficulty is that there is a lot of uncertainties because you don't know many this one, and cost estimation varies with business policy, etc. So to take into account, we did a fuzzy set based modeling, okay, because fuzzy set can handle the data. So first I tell you that in some way that fuzzy concept is not very difficult. That you, what is a fuzzy number? That it is, I am just showing like this in a form of a triangle, one example. And here I am showing membership grade, and here I am showing this one. So it is showing that most likely the quantity is this, that is most likely estimate membership grade is 1, but at 0.5 membership grade it can be here low estimate and high. That means it can be from this range to this range. Then it is a fuzzy number, is like interval number. Many times people say they are, they will get scared that say, how should I use fuzzy thing and something. So but intervals, see, suppose you have to do some estimation. Now estimation can be done using interval arithmetic theory. That is very easy. It is like that, it is as simple as this, that suppose I am going to purchase say some bananas, okay, but I am not sure that in the market how many will purchase. But usually I know that generally I purchase say 4 to 6 bananas, okay. So maybe 4 to 6 bananas, okay. That means either I may purchase 4 or I may purchase this one. If we have this type of idea, everybody has idea. He goes in the market, he purchases some vegetable. So he decides that, that I will purchase this particular vegetable, usually 1 kg, but there his mood gets changed and he said that, no, you give me 1.5 kg. But suddenly he will not do that, give me 5 kg. So that means he has some estimate. So that estimate can be taken. So you can say worst case how much he will take. Sometimes he may purchase half kg vegetable. Sometimes he may purchase 1 kg. Mostly he purchases 1 kg. So that is called most likely estimate. And then sometimes he purchases that, low, that is low estimate, and high. So suppose he has this idea, then price will be uncertain. Okay, suppose he will say, suppose let us say, take an example of vegetable only. It may be 40 rupee per kg, or it may be 35 also. So he takes 35 into lowest estimate. That means suppose he is very lucky and he will purchase very less quantity. Then that will give some number. And then he takes another case that he will purchase 1.5 kg. And then he will take that price maybe 45, not even 40, maybe 45. Then what is that? So he gets a complete range. So that means this data is available with him. That's it. And then he tells to his, that wife, that you please give me this much amount, because that worst case this may be this one. Even he makes the budget. He has both the idea that if he is lucky, he will have to spend say 60 rupee. Otherwise, if he is not lucky, he may have to spend 80 rupees, like that. Similarly, the company, naturally, company has to decide, and it is a big organization. So they have to get some idea. So uncertainty estimate is must. But here the fuzzy set is giving additional, that it tells that this interval is this much, but for that chances are less. Rather, suppose more chances are that the material will be between this to this. So it is generalization of interval number. That means interval arithmetic is generalized. That means you also get this one. So then you just do that. Once you obtain that, suppose you have got low estimate, high estimate, and most likely estimate, then you can make a triangular fuzzy number like this. These estimates can be given by some expert or based on your experience. And then casting can be done by doing the interval arithmetic. Okay, that means that is fuzzy arithmetic. So suppose there is A is some number, some triangle, B is another triangle. If you add them, then A plus B gets added. That means top gets added, bottom also, that worst case, best case, best case. But in subtraction, it is reverse. So there are some arithmetic operations. Those type of things you can always get when you have interest in that. But so we considered example. So we considered milling cutter, we considered 3D part, and we decided what is the bounding box, and we collected the machine specifications, okay, like what is the distance traveled by roller, what is the layer thickness, and all those type of things. What is so if you consider 1 unit of the part, estimation of build time. So we estimate the build time considering 1 unit, and this I did in a deterministic way, okay, in this one fixed quantity. So suppose I am making this one, so my build time came 2.24 and his came 2.29 somebody had done, and this is 1.52, like that. And then once if I make two parts, my build time gets reduced, okay, because that is this one. Then I consider casting, so I consider that this area of operator and all those type of things. Then I can overhead cast, then I do that, but then after doing that estimate, I am now doing fuzzy estimate, okay. So I am telling that time delay between successive layers may be 4 seconds, 5 seconds, or 7 seconds. Like that, everywhere I am uncertain because I am a management guy. I don't know that what will be the layer thickness, etc. I am just trying to assess that whether for our product 3D printing is okay. Then I decide that whether this will be this thing. Okay. So this is so it is slicing software cost, yearly maintenance cost, annual factory rent cost, all fuzzy. And then the total cost of the part also comes as a fuzzy number because you have done the arithmetic operation. So for part one, I got, suppose 26 is the most likely estimate, but it can be 31 also, and it can be 24 also. Like that, I get a data. So I can graphically represent that. This is the cost of part A, this is the cost of part B. I can do that. And then there is this one, I will not tell much detail about that, but there is you can find out the reliability of your estimation also. So I am using the concept of the entropy. Entropy is a measure of uncertainty. So, based on the Shannon's entropy, I am writing some expression, and finally I am doing some estimation that details. If there is a sufficient time and only we pay attention to that, we can do that, but there is some mathematics, and by that you can do that. You can find out the reliability index. So that means finally we get this type of output, that suppose part one is there, okay. So we say that it can be made in $30.9, but that reliability of my estimate is only 35%. That means if I am very lucky, but it can definitely be made in $35.5. For that reliability is 99.97, and if it is $37, then it is 100. So that means your reliability keeps on increasing. Similarly for part two also. So graphically, if I show that you ask me that what is the total cost of a part, you ask me as a manager, suppose you are my boss and you have to set up industry and I am doing cost analysis. So you say that, oh, tell me that what will be the cost of my product. Then I will say, well, this is the cost. I will show a graph. So that means, well, if you pay me 36, surely it will be made, but it can be made in this also, but that I am not sure. It's about, I am something like sort of 0.9 confident or 0.8 confident, so it can be. So businessman will have fair idea because he after all takes a risk actually. So this type of information will be useful. So basically in this cost estimation using fuzzy, I have done this, that we have taken 3 cost estimates from this one expert. Most likely, which can be most likely estimate is nothing but deterministic estimate, and low and high, but it gives a realistic idea. And then we have made a method for reliability, and this will help in this one. So now once we have made a cost model, then the question came that how we should compare it. Now can we compare now 3D printing with our traditional manufacturing process? So we compared it with one injection molding process. So we published one paper, it is in Journal of Advanced Manufacturing Systems, in which Professor V.K. Jain is editor. So it is, since he is editor, so we have submitted a paper there, and this was published here. It is in this we are showing that the same part can be made by 3D printing as well as by injection molding. But in injection molding, you have to make die and all those type of things, ejector pin and complete process is there. So deterministic cast model for injection molding, that how should I find out a cast model? Forget about fuzzy set, fuzzy can be incorporated later. But even doing the cast model, when I started doing that, then we found that it is not easy task actually. It's not very easy. Okay, you can do that. Companies, they do estimate, and the estimate may be wrong. Suppose they are lucky, then they get an extra profit. And if they are not lucky, then they get sometimes loss also. So cost estimation is not that easy as we thought, because we thought that suppose even if you make by injection molding, material cost, mold cost. Now in mold cost, there is a mold base, that means raw material, plate, etc., and then mold manufacturing. Then processing cost, operator cost, labor cost, overhead cost, setup time, cycle time, number of cavities, etc., means how many product at one time they will be made. And then production yield. Production yield is a term that suppose I make 100 components, maybe 10 may get waste. So my yield is only 90%. Okay. That means wastage also has to be considered in the casting. So we have that expressions like C material cost, cost of injection molded part, C mold divided by N. Same mold can make suppose 10,000 components, good. And C processing, that means other processing cost. Okay. Now material cost per part. So this has to be done by this one. You have to consider some losses. So that loss also has to be, LS means some loss, I think. And C mold means mold base, mold manufacturing, and mold base, that how should I find out the cost of that? It is again, there was some empirical expression which we took that some papers of Kalpak Jian actually. Okay. So that means it has come from industry. It's not that it is proportional to thickness, and C processing means many other components. Okay. So that what I am telling, that cost of mold manufacturing. So based on Boothford paper, that manufacturing time in hour for ejector systems, ejector plus pin. So they have given empirical expressions. Okay. So very fact they have given empirical expression, you understand the difficulties. That means this is not so easy, and it has to come. Nowadays machine learning etc. can be used, because if you take database, then you can. This is geometric complexity of the part. So for that again there is some expression, and then measure of complexities for both inner and outer surface, and total time for manufacturing one cavity and one core. So this then injection time, or how much time will be needed to fill up that. So you have to find out injection pressure, and then based on that you find out the time estimate. Roughly you can use Bernoulli's program, that velocity is how much, but you have to use some constant. Then estimation of clamping forces. Clamping force roughly can be the this one projected area into pressure, but then you have to put some constant. Then cooling time. So based on some crude analysis, this one, so there are two time estimates. One is this, one is less, and one is more. So these type of thing analysis models are there. Okay, so then so all this has to be done by, suppose you have to consider uncertainties, then you have to do that by means of this one fuzzy one. Okay, now then your demand also may be uncertain. So it may follow uniform distribution, it may follow Gaussian distribution. So you have to find out, estimate, expected. So it is based on the probability theory. So we considered in the model that aspect also. And then we took all these type of things, and again for two parts we calculated many things. Okay, that means overhead cost. I will not, this one I'm just showing the data that yes, So many things I had to consider, but you know, number of surface segments and this one and all these type of things. And injection pressure, it can be here, it can be this one. Cooling time estimates, two estimates were there. So I took both this one. Finally, the net result of doing all these things, those type of things, you can do calculation in an Excel sheet. And finally, you can get this one. Suppose you have quantity of part is only less, then it is this one, but with more quantity in 3D printing, the cost comes down, but not drastically. That means cost of maybe 5 product is also same as the cost of 30 products, but in this injection molding, the cost comes down drastically. Okay, so if you just have to make one component in the injection molding, then you have to pay 600 rupees, whereas in this case you have to pay only 30 rupees. So see, so instead of 600 rupees you have to pay 30 rupees. So it is like that. But suppose you have to make so many components, then injection molding is coming cheaper. And this is what that another product, same thing. So these are the estimates, that uncertainties are there. So you know, very interesting type of observations come. Even reliability thing also comes, that what is the reliability, this one. And this is uniform distribution, normal distribution. So we got that some interesting result, that suppose you do a deterministic analysis, then from SLS I am getting 3.13 rupees or dollar, and from injection molding you are getting 3.20. So naturally that SLS process is better, it is economical, fine. And it is up to this, even if there is some uncertainty, then also is this one. But suppose uncertainty is more, suppose you know, you have to consider the worst case scenario, that no, as I am thinking it will not happen like that, then injection molding becomes better. So that means your decision also changes. In deterministic analysis you are telling SLS process is better, but in probabilistic analysis you are telling injection molding is better. So this one, so this type of decision has to be taken, and this is based on this one. And another thing is that now finally after doing this thing, then we thought that I must present some analytical method for assessing the utilization of additive manufacturing in an organization. This paper we published in only Journal of Institution of Engineers. And here what I am telling, that I am just defining some parameter, that how should a company decide that his 3D printing in his organization will be useful. So we say that time required for production, and this is total usable time. So we use utilization factor. So if utilization factor is less than 1, that means machine is underutilized. At least these factors the companies can keep. And then they say, okay, this is underutilized, so management should plan to get job orders from outside. Otherwise, unnecessary overhead is getting wasting. In fact, most of the companies now, they are underutilizing 3D printers. Okay, in many academic institutes also, they have purchased the costly 3D printer, but most of the time it is closed. But if utilization factor is more than 1, then the machine is overutilized, and management may have to outsource the jobs or plan to procure additional machine. And then they may have some policy or this one. It's that you can run the shifts, etc. So you can say that maximum utilization factor can be how much, that estimate can also be obtained. Okay. So it is like that. Now you have to say fundamental cost formula can be written as that, depending on the utilization. So we get a cost term in which utilization factor is also coming into account, because otherwise when we calculated the cost, I assumed that machine will be entirely used. So we say that per year cost is this much, but I am taking only 1 hour. So I did it like that. But suppose my utilization is not there, then I have to recover the cost in that time only. That means whatever idle time is there, that will also be this one. So you will get a utilization time, and similarly mean flow time also can be found by this one, and tardiness of the job can be obtained. Tardiness is defined as the difference between completion date and due date, because that can also become a factor. Maybe that injection molding is economical, but then the thing is that if making it by injection molding, you may need 20 days because mold manufacturing, etc. But here you can do 1 day also. So that factor can also be taken into account. Okay, so that means then we incorporated the uncertainty in the same way, the fuzzy one, that there are a lot of uncertainties. Even utilization factor can also be there. So we said that sometimes the machine is underutilized, and but sometimes it will be difficult to know that whether the machine will be underutilized or overutilized because of the uncertainty. Because one estimate can be that it is underutilized, but worst case scenario can tell that it is overutilized. So you will have these type of scenarios. Okay, so these analysis has been done. Okay, now this one. So and then finally you have to decide that whether I have to purchase that a 3D printing machine. So you can take decision based on several criteria. Okay, and in each criteria you can have, it is like a gray relational analysis only. I don't know why there is so many people just write in gray relational analysis and they say gray relation grade, but it's basically simply the fuzzy membership grade, and it is basically, it goes like that you have some this one, and you can have say some membership grade for one criteria, membership grade for another criteria. So you can have two type of strategies. One is called non-compensating strategy and another is compensating strategy. Non-compensating means that if I am good at one aspect, I cannot compensate for the other aspect. So suppose I am in one aspect, cost point of view, my grade is 0.8, but environmental production point of view, my grade is 0.5. So overall grade will be 0.5 only. But in compensating, it can be product. So one can use either compensating or non-compensating, or it can be weightage of both. Okay, weighted average of both. Okay, so this type of thing is there. So we have considered, say, some example that that 3D printing machine we are using SLS, and we are comparing it with this one. So cost of producing polymer cutter, and we have seen that suppose the machine utilization, etc., and we are getting the utilization factor. So for 1,000 units it will be different, for 1,500 units it will be different. So like that, and unit cost will also depend on this way. So what I am telling, that suppose you have annual production unit 100, then the cost is this, but if you have 1,000, then the cost will come out to be this. So worth noting fact is that an increase in the quantities of one part reduces the cost of both the parts. So suppose a company is selling some product, and in one product that company is making some less profit, okay, and another product he's making more profit, but the product in which there is more profit, for that demand is less. Even then, suppose the another product gets sold, then also the overall cost gets affected because utilization will involved. Because if machine is remaining idle, then that cost has to be distributed to both the people, actually, both the cost element. So this is the advantage. So that means when a company has to decide procuring a machine, they have to consider all the aspects, that how many products will be made, how many things will be done. So here there are example that suppose the lot size is 1, then unit cost by injection molding is this much, very high, 8,000, and 3D printing is this much. But suppose lot size was 1,000, then it was 10 rupees and it was 23 rupee. Okay, so that means in that case this was this one. And overall cost, we considered cost and how much time it takes, am giving example that suppose cost and time, okay, both ways we have done. So overall, which one is better? That decision also can be taken. Okay, so process taking the minimum time is assigned a membership grade of 1. Each delay of 1 day is assumed to reduce the membership grade by half. Like that, some logic can be used. Okay, so increase in the production volume of a part increases the utilization factor uh, in the unit cost. Okay, the uncertainty in the unit cost for high production volume reduces due to the low impact of overhead cost. Okay, so that means if you have high production, then uncertainties will also not have much effect. But the production of two different parts, the increase in the production of one quantity decreases the cost of both the parts. This is due to overall utilization of the machine. And then the comparison of 3D printing with injection molding demonstrates that decision to choose one process over the other is dependent on the production volume. For higher lot size, injection molding is preferable due to low production cost as well as low production time. Okay, so that means that aspect is also there, because 3D printing also nowadays naturally it takes time in that sense. So sometimes overall time may be less if you are making only a few products, but if you are doing mass production, still the other manufacturing processes are much faster. Okay, so that is why that lot of, and finally that we said that we have to pay attention to energy consumption also, because ultimately your this one energy is consumed and it will put pollution in the environment, etc. So that for the energy consumption, this will be this one. Suppose you have got one say cellulose. Now you see that you have to heat it. So you have to put a heater here. Resistive heater is there. And then you have got this one movement of the roller. And then you have got a laser sources and all that thing. So you have main energy sources are what? Where are the main energy sources? That laser system, then heater system, then rotating rollers, and then pistons. Okay, so all these energies have to be considered, and we considered all these things with the same efficiency. And for resistive heater, how much you have to see that what is the heat capacity of the powder, and then for the roller you have kinetic energy and all those type of things. So here also how much force is needed, that also is a question. So we have written that FR is approximately 20 times the total weight of the heap of powder generated in front of the roller. This is again based on the literature. Otherwise, you know that if you start doing that analysis, that itself becomes a full task. That means you know that how much force will be needed. Okay, but anyway, this some empirical data is there, because depending on the powder, and then you have to take this one, then some extra energy is also needed. So if you take the estimate of the energies and then you say that these are the parts, then you estimate the, you know, that energy consumed. So table the mass may give some indication about the energy consumption. Okay, so we say that based on the mass, and but it also depends on the part complexity. So we don't know that it is based on the part complexity also. And then we can again do the fuzzy type of analysis, that because there are a lot of uncertainties, so most likely estimate is this, but energy can change from here to here, and we have big variation. And now this is showing that quantities of part B produced and versus the energy. Suppose total energy consumption and per unit energy consumption. So we are seeing that if I make more components simultaneously in 3D printer, then my total energy will increase, but per unit energy will be decreasing. Okay, so that means it is decreasing. But otherwise, if I make only one or two components, then my energy will also go. So we have estimated these type of things, energy consumption model, with a specific example of a cellulose we have shown, and the energy consumed for building a single part and multiple quantities of the part is estimated, it is observed that the maximum energy is consumed by the heater system. Okay, heater takes the maximum amount of energy, and when full machine chamber is utilized, then energy consumption is less. Okay, so that means you have to do that. Okay, so these are the energy assessment, because then we have done something about sustainability assessment. As an example, that FDM was taken. FDM is a extrusion based process, and then we calculated the time estimation there. Time estimation of FDM also is complicated. In FDM, most of the time when we make the parts like I am making, so this machine makes like this, that suppose you have to make some component, a cube type of thing in which there is a hole. So what they will make, that they will make two layers of the boundary which will be fully dense, and in between they will make a porous type of thing, because they say that infill density. Okay, so they make it very light and less consumption of material is there. So if they are doing this type of thing, then a lot of complication comes in the calculation also. Like building of outer surface bounded by rectangular ABCD. So this means that for that you have to consider another type of movement, but in between inner surface also they make, and in this also the similar to SLS. In SLS the roller was moving, here the nozzle is moving, but kinematics wise you can make it in the same way, that if you have this path it may go up to this one, means initially picks up, then it becomes constant, and then this one. But suppose there is not that much traverse, then it will not reach the full speed. Okay, although the full maximum speed in the machine has been specified 600 meter per second, but it is not necessary that most of the time you are running at 600 meter per second, because there is not that much space, because it is going in zigzag manner. It goes and then it stops. So you have to consider that. So for outer boundary, you have this one, inner surface, this is this one, and time taken in step 3. And so this type of thing is done, and this is 100% infill density, and this is say partially field density. So it follows zigzag type of path. So it has to be considered. So all that is considering is very difficult if you exactly want to make a very detailed model that where it is moving. It can be done, but it has to be integrated with your SLS file and whole programming. So we are taking some approximation type of thing, like you have, suppose we think that we are making a cube type of thing. So we say that is the bounding box. And suppose part volume is less, so we find out some parameter rho. That means rho is the V part divided by VB. So rho may be 1, or it may be less than 1. And so bounding box is an imaginary smallest cuboidal shaped box that touches every edge of the part. So in ideal case, the time taken to this one, we say that this is the ideal time L, but we find, but since it is moving in the zigzag function, so we put a correction actually, that C is equal to this much. So a correction factor has been obtained, and that correction estimate is that by finding out the average length. Okay, because that means we are telling that this stage, and then we find out the time for printing. We take various type of this one, that positions. So accurate estimation of correction factor, which we are telling acceleration factor, is a difficult task. So we obtain what will be typical length of movement, that has to be obtained by some statistical approach. So we just discretize the whole geometry into number of components, and we scan at various places and then find out the average length, but we find out the standard deviation also. So we find out the confidence interval, that means length may be this to this, and depending on that, we take the decision. So this was that done, that we developed this type of model, and after making that model, we also did this one, that we did some experiments in our in-house experiments. Okay, we have a fused deposition model, and by this company, that level RL200A, and we took some product and we make various type of things that we have to say. It is not that one model has to be tested for various components. That suppose there is some cube and then there is a hole. So overall bounding box is this, but part volume is this. And another one is this type of product. Then the third one is like a pyramid type of thing. And then this one is like Ganeshji. Here Ganesha is there. And this is a milling cutter type of thing. All these products are there. And for all these products, we do estimated the time. So for part one, it was estimated total time was 76 minutes, but actually it took 73 minutes. Okay. So similarly, there was part two, it was 65, but actually it was 64. And for part three, it was 46 was estimate, but actually it took 47. And then it part four, it was estimate was 49, but it actually took 54. And the part 5, it took 83.72, but actually it took 88. Okay, so that means some error is there in the estimates. And now we can do that interval estimation also from the printing time. That's the part parameter, say something like that, total time. Okay, so we say that it is 72 to 77. That was my estimate, and it came 73. 76 is the most means confidently was estimated, but then there is error. But then the range is this. Another one 62 to 68 was estimate, but actually it took 64. The third one 44 to 48 was estimate, but 47 it took 47 minutes. Then there was 48 to 51, but it took of course 54. That means in this case even high estimate also it classed. Okay, so this type of thing. And even in the part 5 also estimate was something 87.74, 88 only, and we got 88. So almost we can say it is this one. So this type of thing. And then you estimated, once we know the time, then cost was estimated, material cost, operator cost, rising cost, overhead cost. Then energy consumption was considered, energy consumed during melting of filament, energy consumed during extrusion, energy consumed in heating the base plate, energy consumed by movable platform, and miscellaneous consumptions, standby losses, etc. And we put that formula, energy consumed during melting. So we use this formula, energy consumed due to extrusion, that how much extrusion pressure, etc. So we know the viscosity of the material is dependent on the shear rate. So we took this expression. Okay, this type of analysis, if you want to do that, better study the injection molding literature. Okay, because this is a new area, you will not get many papers on that. But that concept can be borrowed here in FDM. So we took that, suppose pressure delta P1, delta P2, and all these type of things. And then energy consumed by heating, this one, and miscellaneous energy consumptions. So this type of things should be estimated the energy, and based on that we can know that how much is CO2 will be emitted by using some empirical expression. But then finally, sustainability means you have to consider social issues also. So let us discuss something about social issues, that working hours and conditions, and how much labor it has to be done, whether those powders will be this one harmful, and then employment opportunities. Suppose we require less skilled operator, but then workers have to settle with the salary of low skilled jobs, because they don't, because CNC machine operators used to get high salary, but here they will see that once a sales file is there, then operator doesn't have to do much. And then health issues are also there, because we are using some chemicals. Okay, so all these issues have to be considered. And authorization and legal issues means what will be the copyright issue, what will be patent issue, and how you can protect this one, and which type of things can be manufactured. And suppose you are, as I was discussing, that you can reduce the time. So time for conventional manufacturing was this much, but for 3D printing is this thing. So suppose TC is say 100 minutes, but 3D printing took only 50. So that means 2 minus 1 into labor cost. So this much labor you have saved. So I am telling that it is a labor penalty cost. So that labor should not suffer. Companies or legalization should give this type of thing. Okay. Similarly, organization can reduce the labor penalty cost by enhancing the production, provided there is sufficient market for the product. If the companies can produce more, then of course they can. Means what I am telling that I am advocating for that type of strategy from government and from some other organization, that suppose your company is there and that company has got 100 labor. Now you start using 3D printing, so you no longer need 100, you need only 50 labor. So you can very easily, you can be very happy and you can pay huge consultancy to me that, okay, 3D printing has been done and it is like that. But this will not be satisfying to me, okay, because you are 50 laborers have lost their job. Instead, you increase the production market. So 100 labor should be 100, but you are producing, say, suppose 1,000 components in a year, now make 2,000. So you increase the market. So this type of strategy simultaneously should be done. Only then we should go for that. So we estimated some case studies we did. We made this Ganesha and Cutter. And then after that, we have done some calculations. Okay. Estimation of energy consumption also we did. Mathematically, it is this one too much. Numbers are there, fuzzy arithmetic in energy consumption and overall. So we said that we consider 300 days in a year and 3D printer operates for 6 hours a day. And based on the assumption, the maximum quantities can be, we did this one, a maximum of can be, and finally the manufacturing cost can be estimated. Then amount of CO2 emission was calculated by energy input and multiple kilowatt hour per year. That means kilowatt hour means 1 unit. So how many units per year, and multiply by emission factor. So emission factor is taken as 0.5. Okay, that unit and this one. So you get amount of CO2 estimation in kg. Okay, so you get an amount of this one. So we are making one part and 2,000 kg quantity of, I think that Ganesh ji here. No? That, you know, is it Ganesh ji? I think part one was Ganesh ji. Yeah, Ganesh ji. So for Ganesh ji, you need this much energy cost. That means basically 45 kg CO2 will be emitted. And similarly, part 2, that, you know, if you make this one, then 34 kg will be emitted. So this also has to be, so that means we should put a penalty on these also. So they can be positive, and then environment social penalty, that means labor cost. Also the penalty due to CO2 can be added to environment cost. So that means you can do the overall cost analysis. So basically, in the context of economic sustainability, the cost estimation we carried out a procedure for estimating the build time we have given, and maximum energy is consumed in heating the base plate, and some aspects of social sustainability have been discussed. And procedure presented can be used to quantify the overall sustainability based on the overall cost, CO2 emission, and involvement of workforce. So you can develop some sustainability index actually, and it can be, so this work can be implemented in industrial scenario to compare various conventional process, and then you can see that which process is more sustainable. Okay, so these things I have discussed, and I think that this is basically the last slide. Okay, so I have discussed. If there is some time, if we have some questions, then we can discuss. I think I may unshare my presentation if you want, then you can see that. Yes, yeah. So this is okay. Well, very
Thank
nice
you
one.
for a beautiful presentation, sir. Participants, if you have queries, you can ask to sir right now. We'll be happy to answer your queries.
Yes. Anything you want to ask, or any this one? Okay. So yes, if they have